let's start. It's my title. Maybe more precisely, it should be like this. And 2 points. I think about gratitude. The first, it is very nice that they invited me. The second, I would like to mention good organization, and the third point is that it is a really good idea to organize a program on this topic. I should excuse that I will present neither finished nor published work actually, but I hope that it will be interesting for you and useful for me. Yes. Today we'll consider one of the simplest systems, two identical particles here, which mostly fermions, but we can also consider two non-interacting bosons as well, and they interact via the zero range potential with the third different particle. It is really one of the simplest systems, and it is amazing that how rich its behavior turns out to be. Well, of course, there is usual motivation to consider the system. It is closely connected with huge expansion in the field of ultra-cold quantum gases. Now, it's my plan. Actually, I think 3 points are important. When I introduce the three-body zero-range force, actually, introduce very simple model how we can simply describe it, and present some numerical values. And maybe in the last part, I could say a few words about something like a conclusion and outlook. Now about short introduction to history. Actually, as far as I know, the first work belongs to Efimov himself, and he proved that for this very system, if the mass ratio, if you remember, it is a ratio of masses of identical particle to the distinct one. If this mass ratio exceeds some value, which is written here, again, Efimov situation takes place. Maybe it is better to say the Thomas situation, but I don't distinguish these two effects actually. Next important paper, at least for me, was the paper of Dima Petrov, where he calculated zero energy three-body recombination rate. It was very interesting paper in many respects, but for me it was it had influence for me for the following reason. Those time I recognized that we actually we know nothing about this system. What will happen if the mass ratio is below this critical value? There were many papers which reiterated the Efimov's result, actually, that there should be Efimov effect after that. But what is below? For example, of course we know that somewhere here there are no three-body bound states. After this limit, there are infinite number of bound states. Well, the simple question arises: what is in between? But it was a motivation, and after that, when you ask the question, now it is only technical problem to calculate something. And we calculated and found that there are no bound state at all for negative scattering, two-body scattering length, and there are one or two bound states here. They are plotted. One state appears at mass ratio 8 and something, and the second one appears at 12.9 and something also.
Should the statement be that there are 0 or 1 or 2?
Zero what?
0 or 1 or 2? Or can you go back one slide? Is that the accurate statement, or is it for a greater than 0 there are either 0 or 1 or 2?
You mean scattering length?
No,
What is scattering length in this picture?
This is the scattering length between the two distinguishable particles. But
yes.
You
The interaction is turned on only between different particles.
You say if A is greater than 0, there are 1 or 2.
Yes.
But 0 is also a possibility, isn't it?
Yes.
0 or 1 or 2.
You mean two-body scattering length?
Can you back up one slide?
Okay.
Yeah, I'm asking if the statement there is accurate. For A greater than 0, is there either only 1 or 2? Or
No,
0
no. For A equals 0, you mean?
0 and 0.1.
Well,
0 below 8.17.
So it should be 0 or 1 or 2.
yeah. In principle, yes. A should be 0 or infinity, or 1 or minus 1.
No, he's talking about the mass ratio.
So,
as the
yeah, there's no bound state if the mass ratio is less than 8.17. There's one bound state between 8.17 and 12.9.
Yeah.
And
So the
then
statement is not accurate on the previous slide.
2.
But what is not accurate?
12.91.
Well, okay.
You excluded 0 as a possibility, but 0 is one of the possibilities.
0 value of what?
0
Number
bound
of bound
states.
states.
Yes, it is possible. Below this mass ratio. It is not plotted on this picture. Here, well, okay. There are no bound states here up to 0.
Maybe you could use the solid pointer. I can't see your little dot of light. Can you use a? Yes, that would be much better.
Here is mass ratio axis. Below this point, there are no bound states at all. There is one bound state in this interval between these 2 points, and 2 bound states in this interval, and infinite number of bound states above critical value.
Again, may I ask, what is the scattering length that you discussed now?
Actually, I put it equal to 1. Actually, I will say about it, we can use it as a unit of length. So actually, here the three-body energy. Excuse me, would you like to hear my answer? Actually, the three-body energy is measured in terms of two-body binding energies. If you put the two-body scattering length to unity, it's just a length scale, nothing else. But probably it will be more clear below when I write few equations. Well, also it was obtained that the same picture is present for higher partial waves, for higher angular momentum, something like that. Here is again the case of total angular momentum 1I. I forgot to say that it was, it is important. I forgot to say that for two fermions and a distinct particle, three-body bound states arise in this bound state are of angular momentum 1 and parity, of course, negative in this case. For example, if you go to two fermions, but in the states of total angular momentum 3, we found that, of course, critical value where Efimov effect takes place is about 76 or something like that. But before it, we obtained 4 three-body bound states. So for total angular momentum 3, 4 bound states arise before Efimov situation takes place. Let's go further. Also, actually, there were a few more papers which confirmed that these states actually exist. And now I went to actually to beginning of my talk. The problem, there is one problem in all these considerations. Actually, as we shall see below, we can construct square integrable solution if mass ratio is within this interval. Maybe it will be more clear when I write few equations. And in this respect, it is clear that formal problem which we consider does not actually correctly defined. It does not correspond to any self-adjoint Hamiltonian. That is the problem. And it is, I think it is necessary to consider the situation in more details. In principle, it is similar to Efimov situation when also you met this problem. Near the zero collision, near the triple collision point, your potential becomes singular, and wave function is wildly oscillating, and you need to introduce additional parameter. In principle, here the situation is the same, and I'll try to show you why. In principle, it is the essence of my talk.
So in this regime, there is this problem of self-adjointness. So if you go with mass smaller than 8.6, then
there is no this problem.
after 8.6.
Yes, before,
But
below.
above that.
Yes, and above the Efimov situation takes place.
What are the critical values, lambda 1 and lambda 2?
Lambda 1, lambda 2. Well, I will show it on maybe on the next slide. Yes. Lambda 1 is this value. This one. And the bound I mentioned is here. So there is a small window where this one calculated bound state. Well, there is no difficulties at all. Okay, let's go further. Actually, this very problem was somehow discussed in these two papers. We know authors, at least some of them. And I should mention also that there are a few, or maybe even now even many mathematical papers. I just mentioned papers by Minlos because I read it. I read them, and because Minlos is one of foundators of all this zero range, of the mathematical approach for all these zero range potentials. Minlos jointly with Fadeev, and probably you know their old papers. Well, now let me introduce some notations. Again, two identical particles, mass m, and distinct one m with mass m1. We introduce scale Jacobi coordinates. Here are units. Absolute value of the two-body scattering length will be put as 1, just to have this length scale. This means that two-body binding energy is always 1. So any energy is measured in this value. Now we comes to, in these variables, we comes to very simple and pure mathematical problem. We just have free Hamiltonian for free motion, and impose a simple boundary condition, and impose that the requirement that the wave function is antisymmetric because they are fermions. That's all. Now we have to find how this simple system behaves. Actually, I should say in advance that full answer is not known. Well, okay, let's go further. It is clear. Now I'll introduce specific expansion, which is probably most of you well know very well. Actually, we solve the equation on hypersphere with this boundary condition now, and with the antisymmetric requirement of an antisymmetry of the wave function, and expand on these functions, expand total wave function on a set of these eigensolutions, and comes.
So what's that equation? What's the meaning of this? Is this a wave function?
Which one? I don't hear.
This is the middle one. This equation.
Here?
Yeah, this equation, yeah. What's the, I mean, this is the whole equation. Where does it come from? From this boundary condition. Oh, okay, two-body.
Yeah.
Yes.
And now we obtain an infinite system of coupled ordinary differential equation, and actually we will study the first one. Because eigenpotential in this equation are enumerated in increasing order, so the first one will be most important. Okay, now it is, well, these coupling terms could be calculated exactly, and we know that there are no problems with them. Well, the solution is very simple, again, and this eigenvalue is just a solution of this transcendental equation, where I introduce convenient notation for the mass instead of mass ratio omega. For example, let us apply it just for example. If you put hyperradius equal to 0 and try to find at which value gamma becomes 0, we immediately obtain this simple equation which determines the Efimov's value.
So physically, when you take your hyperradius to 0, this effectively corresponds to a very, very large scattering length, right?
For example, or if you like, we consider zero range model. So if the scattering length is any finite, is of any finite value, anyway, you have to go to 0 because of zero range model.
Sorry, maybe I missed. So if the rho is 0, I can let why did gamma go to 0?
Well, yes, that is what. Well, let me explain. The first gamma, the lowest gamma, if it goes to 0 here, so we obtain exactly the equation, second derivative, and well, here plus 1/4 of rho in exponent -2. That is critical value where infinite spectrum arises. That is why we have to find the condition for gamma equals 0. Now, also in the following we'll be using simplifying notations. And now maybe the most important part of my talk. In fact, if you consider the behavior of the above differential equation, it is easy to see that the solution could be expressed as a linear combination of regular solution and irregular solution, which with arbitrary constant. That is, and both solutions are square integrable in this case for this mass ratio interval. So we can put here arbitrary value. And this is the problem, that why we can construct the bound state solution with arbitrary energy. So what we should do in this situation? We have to impose a condition that these coefficients acquires a definite value, and select from the family of Hamiltonians only one Hamiltonian for the prescribed value of this constant. Only limitation on this constant is that it should be real to provide the self-adjointness of the total Hamiltonian. That's all. Now I decided to express it in this form, just to have B dimensionality of length. Now B is length. And otherwise, we can, for example, multiply it for any functions, any function of mass ratio. There is freedom. It is just my definition, nothing else. I think, as we shall see later, I think we can call it generalized three-body scattering length. But now solution is uniquely defined by this value. That is the most important, and we can investigate what will happen for every value of this B. And actually, B could be, as you know, scattering length can be positive or negative. So I introduce the convention that we will say that B is positive if here is minus sign, and we will say that B is negative if here is plus sign to match the usual definition of the scattering length.
So why don't you allow gamma to be between 0 and 1?
It doesn't matter actually, but in this interval, I can write this simple form. You will see in the next slide the other cases. Let's, sorry?
If gamma is larger than one half, then the wave function would diverge at low equal
No,
zero?
no. Oh, yes, it is of course, but anyway, the wave function is square integrable. That is the point. It can be divergent. Or doesn't. Okay, let's go further. Yes. Now you can see another cases. Why I separated these cases? Simply because I should include one more term in the irregular solution, from the irregular solution. I cannot skip this term. In this case, this term is diverging. Well, this term is greater than the regular solution, so I have to take it into account. For two limiting cases, gamma 1/2, we also obtain additional term. Now it is hyperradius log hyperradius, and in this case, the asymptotics is simply log rho b. That is the reason, nothing else. In principle, is the same.
What is this Q? Okay.
Sorry?
Thanks.
Is it?
Answer my question.
Sorry?
I was wondering what the Q was. Yeah, but
Q I defined as the derivative of gamma squared. Let me show here. Here is Q. I know it is not a good style to introduce notation and use it afterwards. Now let's go to this Q. Okay. Now we construct simple model to solve somehow, at least, to find any, no, not only to solve, to investigate what will happen. And for this simple solution, we simply made 3 steps. First of all, we take only one hyperradial equation, as I said before. Now, we, instead of exact gamma, we introduce gamma at rho 0, gamma squared, and the first derivative of gamma squared. That's all. Only 2 terms, 2 singular terms will be retained. in the expansion of gamma. And also we need a constant which will be fitted from the condition that the solution should match our numerical result. Well, here I tried to show quality of this approximation, but unfortunately it is not, maybe otherwise it is impressive or not impressive, I don't know, because exact effective potential and model effective potential simply coincide on this picture in the most important region, well, for hyperradius now from 0 to 3. But in fact, what we need only to reproduce the correct behavior at 0 hyperradius, where the problem takes place. That is the point. But from this picture, we could expect that model should work very well.
But these curves start to deviate if you go to higher.
Well, they have to deviate, but this is the most important part of where all the wave function is concentrated. Now, I'd like to show that about this additional constant. Here, I just put it to constant. Well, in principle, I can take it differently. Take it as a function of mass ratio to reproduce exactly our calculation. In the case of b equals 0. Well, I have to say it right now that our previous calculation, you can consider that our previous calculations simply correspond to the case b equals 0. That's all. Well, and now we can determine this constant by comparing approximate solution, which I show you below, with the exact numerical calculation. But it turns out that if we put it just constant for any mass ratio, we can reproduce the numerical result reasonably well.
So why is energy a function of Hubble radius?
This one? Well, I derive it from this model. This is model, solution of this model. This simple expression stems from the solution of this simple model, nothing else.
How did you ensure that b is equal to 0 in your previous calculation? What did you do to fix this? I mean,
We in our previous calculations, we put b equals 0.
so you have b as an explicit parameter there also.
Actually, we knew this from the beginning. This problem existed when we calculated, but for the reason, well, actually, we thought those time that it is necessary to calculate something. And it was the most natural choice for this value.
So could I understand your b is 0 case in the following way? So that previously what you've done is you've basically just taken the regular solution.
Yeah, precisely.
And now that means that b is 0, so the admixture of the irregular solution is actually enforced to be 0. And now what you're allowing for is you're allowing for an admixture of the irregular solution. And this means that your generalized three-body scattering length is non-zero. And that means that your binding energies are changing.
Yeah, of
Would
course.
that be one way of looking at what you're doing?
Well, actually, maybe I should say in different manner. Actually, the problem is to construct general solution, to investigate all the family of Hamiltonian. That was the point. Well, and I would like to explain that we can exhaust all the solution by changing this additional parameter b value. That's all. It is the essence of my talk, nothing else. Well, now probably I could explain how we can solve this simple model equation. Well, if you introduce this convenient and simple notation, we obtain very simple and very well-known equation. Actually, it is equation for Whittaker function, and I will express the solution via confluent hypergeometric function. It is simple. But first of all, well, something wrong here. Yes. No. Well, please forget about this misspelling. Sorry.
So here you actually meant a going to infinity.
Yeah, a going to infinity. Yes. I don't understand how it can squeeze. Okay, let's consider infinite two-body scattering length, for example. Now, somebody asked about this this case. This means actually that we obtain very well. This means actually that we should skip this term, and decay at infinity solution is simply Bessel function. This one. From this, we obtained that parameter kappa is inversely proportional to B and corresponds to the binding energy of this sort. So it is clear why I call B scattering length. Actually, we have usual expression for, in this case, two-body scattering length infinite. Usual expression for the energy. Energy is inversely proportional to B squared. As I said above, we can introduce this parameter in different manner. For example, we can require that B tilde should be defined from this solution, so from this equation. So in this case, if we use B tilde, we simply obtain E is equal to -1 over B tilde squared. That's all. It is just to explain that we are free to define this constant. And now let us consider general case. Here I will speak about A greater than 0, but as we shall see later, it doesn't matter. Now the solution is actually one exactly confluent hypergeometric function which decays on infinity to provide the bound state, and here is the result. Parameter B is connected with eta, which expresses via energy by simple expression. Maybe I will show you below that this expression gives us typical typical picture when one long range potential, there is one long range and short range potential, and they have two states or in each potential, and total picture depends on the position of the states, nothing else. In principle, at this point, I could stop and go to conclusion. But we have some time, and I hope I will show you interesting pictures.
So excuse me, how A is it hidden in gamma? I missed something.
Sorry, a bit louder.
So positive A, right? So is it
Is 1
A is set to 1?
plus 1.
Absolute value of A is set to 1. So A is simply 1.
So you measure B.
B in its units, in natural units. Let's go further. If we now, if we study, well, again to this equation, we can easily study this simple solution to obtain, for example, if B goes to 0, energy, there are few states for different n. Actually, I think there are only two states. For infinite B, the picture, it is also simple to find that, well, it is the same as in usual Coulomb problem. Gamma, you can consider gamma as equivalent of angular momentum. Q is equivalent of charge, and n is principal quantum number, nothing else. At least for B equals 0 and B equal infinite B.
So I mean, if I think about the Coulomb spectrum,
Yes, it is Coulomb spectrum.
I think about an infinity of states.
You know,
you talked
but you have a threshold at -1, two-body threshold. So it is scattered from above. Coulomb spectrum consists of many states converging to 0 energy. But in this system, we have a threshold at -1 exactly. Two-body threshold. So from this spectrum, we can only obtain 1, 2, or 3 states, as I will show. Understandable?
Yeah.
Okay. And a few more simple cases. Also, we can easily obtain for this particular cases simple equation for energy. Now, I am proud of this picture. I call it spider plot. Now we can easily solve the above equation and construct and plot three-body energy for different values of three-body scattering length and different values of the mass ratio. Here is at the end of this plot is the limit above which the Efimov situation arises, and here is the lowest limit above which our consideration makes sense. Now let me explain. This thick red line, 1.
Could you use a solid pointer so we can
Sorry?
see? Could you use a stick so we can see where you are pointing?
Okay. this line, thick red line, it is nothing else as b equals 0 calculation, which in principle coincide with our initial numerical result. Here is the second state. Let me recall on this scale of energy. This scale is chosen in order to have infinite values here. -1 means infinite energy in this scale.
Minus.
And 0 means threshold, -1. So otherwise I can't plot it and show how it behaves. Well, okay. Now we have to reproduce previous calculation for b equals 0 case. It is done. As I showed, the ground state is reproduced very well, and of course the model works not so good near the threshold. It is evident from the beginning.
Is that second statement?
Yes, this one. Thick red line.
I thought there were supposed to be two states in this region. Aren't there two bound states?
Yes.
And where?
Here, in this mass interval, we have two bound states again. In this interval, we have one bound state, and somewhere below this point, we have no bound states.
I thought there were supposed to be two bound states in this whole interval from 8.6 to 13.6.
To
No?
certain? No.
No?
There are different number of bound states for different mass ratio, of course.
So two bound states if it's larger than 12.9.
12.9.
Well, and now the solution for infinite B. Thick blue line, we have also two solutions. One of them goes to infinity. Okay, there are many interesting features, but I recommend to take this wonderful picture and ask me later about what will happen. What is pleasant is that due to simplicity of the equation, we can easily plot it. That is the point.
So this picture is now, this is obtained in your, in this model you made.
Mm-hmm.
So is there something special about that point where a lot of curves cross?
Well, yes, actually. Maybe I will say something about it later.
Spider
3131. That's where gamma is 1/2.
Yes, gamma 1/2 is, well, let me return to this question if I will have some time. Okay, actually for the negative two-body scattering length, we can use the same equation also, and I will skip, well, similar, not so nice picture for the negative two-body scattering length looks like this. Again, I'd like only to mention that if you remember, we haven't, for b equals 0, we haven't bound states, three-body bound states from the beginning. But, sorry, now we see that there is actually three-body bound state for this one, solid blue line, for, well, no, not solid, this one, B, this one, between these two blue lines, it corresponds to B, to infinite B. Values for so only one remark. Now, if we change the three-body scattering length, we can obtain three-body states for negative two-body scattering length. That's all. The most important thing of this picture. Now, I wrote here most important points, and here is the point you are asking for. Actually, it is not surprising, because the most singular term in the potential, 1 over rho squared, is either positive above or below. Well, for gamma, it is positive below the critical mass ratio for gamma 1/2, and is negative above, and 0 exactly at this point. So you have to have discontinuity at this point, because the solution, the equation, initial equation, anyway, is of this should be of this kind. This also means that if I will calculate exactly, not in the model, the situation should be the same. The singularity should not disappear. We have the same singularity both in model and in exact calculation. So the behavior, qualitative behavior, and this discontinuity will persist always. Well, okay. If you already read all these points, let me go further. Well, now it's a typical picture how just another kind of representation, how the energy spectrum behave for fixed mass ratio, how it depends on three-body scattering length. We can see that there are at this mass ratio 1 or in this narrow interval 2 three-body bound states. Similar picture for another, exactly for one gamma 1/2 this mass ratio state. Now we can mostly have 2 bound states, and probably in this small interval only 1.
This is 5 channels. You mean you have 5 coupled hyperradii equations?
No, 5 channel. Thank you for this remark. I forgot to say that now it is numerical calculation of the initial system of differential equations. Actually, excuse me, I forgot to say, it was written here. Now I switched to presenting the result of real numerical calculations, not model. But actually the difference is rather small, usually. And one word about channels. This means that we use 5, we truncated the system up to 5 equations. Actually, it is quite sufficient to have 2 or 3, and even 1 equation give almost the same result.
So my natural question, do you have a B for every channel?
B? Actually, it is necessary to impose this condition, three-body condition, only in the first channel. It is sufficient, because in all higher channels, the wave function goes to 0 fastly. There are no this problem. There are no 2 solutions which are square integrable. We can, in all these higher channels, we impose simply zero boundary condition on this at zero hyperradius value. Well, all the same, again, now I try to show that there is discontinuity here. Maybe I say a few words about it. Six solid line, it is exactly gamma 1/2 solution. Gamma 1/2 solution, I see. And if we go to this closer to this point, for example, green, blue, and this I don't know line, the solution becomes green, blue, and this one becomes more and more steep, and it does not converge to the solution at gamma 1/2. The same for the mass ratio above 12.3 something, which corresponds to gamma less than 1/2. Anyway, I have to go further. It is the same picture for near the upper critical value. Here, I should mention only that in this case only positive B are possible. And now I should not show it, but anyway, it's the result of numerical calculation. There are numerical problems here, but otherwise the picture is almost the same as in the model calculation. And some few points to conclude. I hope I explained that this system at this mass ratio range requires two-parameter description. And I showed, I think, how to introduce this parameter. There is more fine question. Actually, this three-body boundary condition means that we introduce the three-body zero-range three-body potential somehow. Well, and what is done? It is shown that we can introduce this three-body zero-range potential in this manner. Well, but should we do it? It is more fine question. Now, of course, there are evident applications where all this consideration should be applied. For example, for higher angular momentum, the situation is the same for other angular momentum values. Also, this situation might arise in maybe in some system in mixed dimension. I think at least I saw few one or two cases, and maybe what is more important is that now we should reconsider also many body, for example, forward problem. For example, in this state, it was shown that the Efimov situation takes place above this value. It is very interesting, but now I like to ask for which Hamiltonian this result was obtained. And let's go further. also I think that it will be useful to understand a crossover problem. How here is the one paper I know. The states we are discussed are here. Authors of this paper tried to connect Efimov, infinite number of Efimov states, with one or two states here by introducing the cutoff parameter, by investigating the dependence of the cutoff parameter. I think that we have to consider it more carefully because not only Efimov trimer depends on the additional parameter, but also these states also depend on additional parameter actually. And here is one of the buildings of our institute. Here is Dubna in summer. That's all. I'm almost at time.
Yeah, thank you very much. Eric?
You said you can consistently introduce this three-body parameter if the ratio is bigger than 8.6. What about between 0 and 8.6?
Well,
You cannot introduce it
between 0
and 8.6.
yeah, there is no reason to introduce any additional parameter. We have not the second solution, irregular solution, is not square integrable. So we have not do anything at all. There are no problem.
I think we can discuss about this.
I hope.
Yeah, so another question. So Petrov had an argument for why normally this kind of parameter B can be neglected. So he argued that usually B, this kind of a parameter, is over the order of the range of the interaction. So for example, near the border fastball resonance, the scattering length is much larger than the Van der Waals length, but this parameter, the natural value of B would be comparable to the Van der Waals length. So do you have some suggestion about how to increase the value of B so that it becomes comparable to the scattering length?
Actually, I should say that, well, simple question is I don't know. But more precisely, actually, it is more important to understand should we introduce this parameter at all. For example, Minlos communicated me that, well, and he wrote this in his papers, it is pure mathematical rigorous treatment. And his opinion is that for gamma greater than 1/2, we need not introduce any additional thing. That he thinks that he proved that Hamiltonian becomes self-adjoint if gamma greater than 1/2. And only in the region gamma between 0 and 1/2, there is a problem. It's an opinion of Minlos, not mine. So I think it is a delicate matter. What we, which Hamiltonian corresponds to the real situation. And in principle, it will be useful, as you said, to study which parameter B corresponds to particular two-body interaction in the zero range limit. But I don't know for which mass ratio we have to do it. That's the way.
Maybe I can add a comment to this that connects with your answer as well. We've done calculations for finite range Gaussian potential, and we've made the range smaller and smaller. And we do see these non-universal three-body bound states.
Universal, actually.
Well, it's a question of language.
The
Whether
value is
you,
very
whether
universal.
you need, like if you need two parameters, whether you call it universal or not. So we do see at a mass ratio of 12.3131 for the Gaussian interaction potential that these bound states do show up. And we formulated a zero range model with a quantum effect theory picture that's very similar in spirit, I would say, to Oleg's description. But we can also discuss that later.
Why do you need to include this 1 over rho term in your effective potential if you want to go to very short distances? Isn't it sufficient to take the most singular term?
Well, actually, maybe it was not clear, but actually, well, now, actually, if you try to define how you should try to define this parameter b, you cannot, at least in this interval, you cannot skip this term. So term with q is also singular, and it should be taken into account, at least to define the very condition which you impose. So I would like to say that this term sometimes is also important. You cannot exclude it.
Okay, but if you say, I mean, you could turn this around and say that, well, if you don't, in order to introduce that parameter, you need to take a term that is less singular, then maybe you don't need this parameter because at short distances you just have the 1 over rho squared.
No, there are no more terms which you should include. It is easy to see. Only two singular terms are important.
Well, I would argue the most singular one is sufficient, but
Here, this term is more important than regular solution, so I cannot exclude it. Anyway.
Term is greater than 0.5. That term is more important than the first.
I mean,
That might
So
short distances, if you have the 1 over r squared potential, and you know that this is not singular if the coupling is smaller than
actually,
-1/4.
excuse me, actually I would like to thank you for this question. I forgot to mention it. Actually, it is interesting point. We cannot exclude the next singular term, for at least for this interval of gamma. And it is clearly written here. It is great. This term is larger than this one. I cannot skip it. Simple.
So maybe we discuss that more during the discussion session. Are there other questions?
What is the formula for Q in terms of the mass ratio?
A bit more complicated. I did not present it here. Well, we can actually, let me show. We can easily calculate it from this transcendental equation. It's a bit lengthy, but it's an analytical formula.
Do you have a plot of Q versus the mass ratio? That will be
Yeah,
helpful.
of course. It is a simple function of, I did not plot it, but I have an equation also in terms of sine, tan, cosine
So
functions.
It's just a function of the mass ratio.
Yes.
Maybe that's also something we can plot during the discussion session. So if there are no other questions, let's thank Oleg
Thanks a lot.
Otherwise, I'll keep on recording.
It doesn't.